Bismillahirrahmanirrahim. Hello everyone, I hope you are all doing well. I welcome you all in class of elementary number theory by David M. Burton. Our discussion is continue on primitive roots and indices. This is chapter number 8 in David book. In today's lecture we will discuss a very nice example. That this example is example 8.2 and this example can be stated as this example says that we have to show if fn is a prime, then for n greater than 1, 2 is not a primitive root of fn. First of all, what is fn? Fn is a Fermat number. This example says that 2 is not a primitive root of Fermat number when your n is greater than 1, and the condition is that Fermat should be Fermat prime number. You know, Fermat number are of two type. It may be both, it may be prime and as well as composite number. For some values of n, its answer is prime, and for some it is composite number. So when your Fermat number is a Fermat prime and your n is greater than 1, then we have to prove that 2 is not a primitive root of the Fermat number. This is our target. Just for your elaboration, I will show that when your n is less than or equal to 1, mean to say when your n is 0 and 1, then 2 is a primitive root of fn. So what is actually what is Fermat number? As Fermat number fn is can be defined as this is 2 raised to power n plus 1, and your n is greater than equal to 0. I will show that when you take n is equal to 0, here your f of 0 is 2 raised to power 0 plus 1. 2 raised to power 0 is 1. This is equal to 3. So here we show that 2 is a primitive root of 3. 3 means f0. I hope at this stage you have a clear understanding about the primitive root, the definition of order of an integer. Otherwise you cannot understand this example. To show that 2 is a primitive root of 3, firstly we will find the phi of f naught. Phi of f naught means the value, phi means Euler-Tauschan function. The value of Euler-Tauschan function at f naught. What is f naught? F naught is here 3. Here we can use the formula. The value of phi at any prime p is p minus 1. This is very simple formula. So this becomes 3 minus 1. This is equal to 2. Actually, phi function shows the number of all positive integers that are relatively prime to n. So it means there are two numbers which are relatively prime to 3. Now if 2 is a primitive root of 3, then its order should be equal to phi of f naught. That is, it should be equal to 2. So here 2 raised to power 2 is equal to 4. Is 4 congruent to 1? Modulo f naught means 3. Yes. What is the definition of congruency? The definition of congruency says that two numbers are congruent to each other if their difference is divisible by this modulo. So you can notice that the difference of 4 minus 1, this is 3, and 3 is divisible by 3. This shows that these two numbers are both congruent to each other, and 4 is equal to 2 square. This shows 2 square is congruent to 1 modulo 3. Modulo 3 means modulo f naught. This shows that the order of 2 is 2 modulo f naught. Hence, 2 is a primitive root of f naught. What was the definition of primitive root? A number a is called primitive root of n if its order is phi of n. That is, a raised to power phi of n is congruent to 1 modulo n. Then we say a is a primitive root of n if its order is phi of n. mean to say its power phi of n is congruent to 1. So you can notice here the power of 2, this 2 is equal to phi of f naught, which is also 2 and congruent to 1 modulo f naught. Further, I show that 2 is also primitive root of f1. What is f1? Here f1 is equal to f1. How we can evaluate f1? By just putting value n is equal to 1 here. This gives 2 whole power 1 plus 1. This is equal to 2. This is equal to 5. Simply. Now, what is the value of phi at f1? This is equal to phi of 5. This is equal to 5 minus 1. According to that result, if p is prime, then its value of phi at p is p minus 1. This is equal to 4. Now I will show that the order of 2 is equal to 4 modulo f1. 2 raised to power 4, which is equal to 16, and this is congruent to 1 clearly, modulo f1. What is f1? My f1 is 5. Again, you can check that the difference of 16 and 1, which is 15, is divisible by f1. What is f1? f1 is 5 here. This shows that the order of 2 is equal to 1 at order of 2 is equal to 4 with modulo f1. If we consider f2 greater than 1, what is f2? f2 is equal to 2 raised to power 2 plus 1. This is 2 raised to power 4 plus 1. This is equal to 17. Now I will show that 2 is not a primitive root of 17. What is the value of phi at 17? This is equal to 17 minus 1. This is equal to 16. 2 will not be a primitive root of f2 if its order is not equal to 16. And I will show that its order is 8. Here 2 raised to power 4, this is equal to 16, and this is congruent to minus 1 modulo 17. Again, you can notice that two numbers are congruent to each other if their difference is divisible by this modulo. 16, the difference of 16 and minus 1, this is equal to 17, and this is divisible by 17. This shows that 16 is congruent to minus 1, and hence 2 raised to power 4 is congruent to minus 1. This shows 2 raised to power 4 is congruent to minus 1 modulo 17. If we take square on both sides, this becomes 2 raised to power 4 whole square. This is congruent to minus 1 square modulo 17, which is equal to 1. So 2 raised to power 8 is congruent to 1 modulo 17. This shows that the order of 2 is 8, which is not equal to phi of 17, and hence now 2 is not a primitive root of 17 as required. But this is not this work is not the part of your question. Now we will prove this question in general. This is just for your understanding, just for elaboration. Now I will prove this example in general. Actually, what we have to show that 2 is not a primitive root of fn. A number is called primitive root if its order is equal to phi of fn. So my target is to show order of 2 should be less than phi of fn. What is phi of fn? What phi of fn, as we have assumed that fn is a prime number. Fn is a prime number. So in case of prime number, the value of phi should be equal to p minus 1. So this is equal to fn minus 1. What is the value of Fn? Fn is a Fermat number. By definition, this is equal to 2 raised to the power 2n plus 1, and this is equal to 2 raised to the power 2n. So I will show that in order to prove 2 is not a primitive root, I will show that the order of 2 will be less than 2 raised to the power 2n. This is our target. As Fermat number can be defined as, here I will use just an identity that is the actually keybone of this theorem, as 2 raised to power 2 raised to power n plus 1. This is my base 2 and the power is 2 raised to power n plus 1 minus 1. This whole expression is equal to 2 raised to power 2 raised to power n plus 1 into 2 raised to power 2 raised to power n minus 1. You can verify this expression just by using the simple formula a square minus b square. This is equal to a minus b or a plus b into a minus b. I hope you can verify this. Otherwise, if you apply this formula on the right side, this becomes 2 raised to power n whole square minus 1. By using the law of exponent, these two powers will be multiplied with each other. This is equal to 2 raised to power 2n into 2 minus 1. As again, by using the law of exponent, as the base is same and the powers are multiplied with each other, so these powers will be added. So this gives 2 raised to power n plus 1 minus 1. So I hope you can verify this expression easily. Okay. Now, if you observe, this expression is actually equal to, this is the definition of Fermat number Fn. So this is equal to Fn, and this is 2 raised to power 2n minus 1, and this is equal to 2 raised to power 2n plus 1 minus 1. This equation actually fulfills the definition of divisibility. What was the definition of divisibility? A number A is called divisor of B, or B is divisible by A if there exists an integer m such that this B can be written as the product of A and M, where m is an integer. This is the definition of divisibility. You can observe that this is my left hand side. This is the product of these two integers. This expression, this bracket is also an integer for any value of n, and Fermat number is always an integer. So this left side is the product of these two integers. Similarly, as b is equal to am. So I can write as Fn divides 2 raised to power n plus 1 minus 1. Although the second number also is a divisor of this number, but I am interested in Fermat number Fn. So this shows that this number is divisible by this number, this product. Okay. Yes. Next, what is the definition of congruency? The definition of congruency says that a number A is congruent to B modulo M if and only if the modulo M divides the difference A minus B. If these are congruent, then it fulfills the definition of divisibility, and if M divides A minus B, then they can be written as in the form of congruency. You can notice here, this number Fn is a divisor of the difference. This shows that the number in the difference 2 raised to power n plus 1 are congruent to 1, are congruent to each other modulo Fn. You can match this definition, this expression with the original definition. This is the divisor and this is the difference of two numbers. So this difference is congruent to each other modulo Fn. Lastly, Sallallahu alaihi wasallam. Okay. What does this expression shows? This expression can also be written as 2 raised to power 2 raised to power n plus 1 is congruent to 1 modulo fn. What is the definition of order of an integer? The definition of order of an integer says a number k is called order of an integer if its power is congruent to 1. It means the order of 2 is 2 raised to power n plus 1. By a straightforward argument, induction argument, we can check that this number 2 raised to power n plus 1 is always less than 2 raised to power n. Where phi of fn, where 2 raised to power n is actually equal to phi of fn. You can use mathematical induction, but there is no need to use. It can be easily observed that this number, that is the order of 2, is actually less than this value 2 raised to power n. And what is this? This is actually the value of phi of fn that I have calculated here. So your order of 2, you can verify this. If you take n is equal to 1, then both left and right are equal. But here n is greater than 1. When we put n is equal to 2 here, the left side gives 2 raised to power 3, that is 8. But if you put n is equal to 2 here, this gives 2 raised to power 2, 4, 2 raised to power 4, 16. 8 is less than 16, this is clear. When you put n is equal to 3 here, this gives 8, and this gives 2 raised to power 8. N is equal to 3 here. This gives 2 raised to power 4, 16. This gives 2 raised to power 3, 8. 2 raised to power 8 is 256. Yes. So this number is again less than this number. So this expression is always less than this. So next we can write as, this implies order of 2 is smaller than phi of fn. Hence this implies 2 is not a primitive root of fn. Hence 2 is not a primitive root of fn, because the definition of primitive root says its order must be equal to phi of fn. But this is not equal to phi of n, this is equal to 2 raised to power n plus 1. So I hope you have a clear understanding about today's discussion. Still you find any question, query, you can message me. Inshallah I will reply you. See you in the next lecture. Take care. Allah Hafiz.